Good afternoon, everyone. I'm Yan Tonglai, a PhD student from Institute of Information Engineering, Chinese Academy of Sciences, and University of Chinese Academy of Sciences. As the first author, I will present our paper, Disentangle Contrastive Hypergraph Learning for NetSPI Recommendation. This work is also done as a research intern at Meituan, one of the largest location-based service providers in China. I will introduce our paper from background, motivations, methodology, experiments, and conclusion. We firstly give a definition of point of interest POI. It's a specific location that someone may be interested and find useful, such as coffee shop and restaurant. Therefore, POI recommender systems have been widely utilized to help users and service providers for exploration and targeted advertising. Among various POI recommendation tasks, NetSPI recommendation is arguably a prominent and trending one. Different from conventional POI recommendation, it considers users' recent spatial temporal context and long and short-term preferences for net-suitable location suggestions. Prior NetSPI recommendation approaches are mainly classified into sequential-based paradigm and graph-based paradigm. The key rationale behind the sequential-based paradigm is to treat NetSPI recommendation as a sequential prediction task and adopt sequential methods to model transitional patterns, ranging from Markov chains to recurrent neural networks and recent self-attention mechanism. However, sequential-based paradigm mainly focuses on sequential patterns mining, but fail to explore collaborative signals, which help alleviate the data sparsity issue. Inspired by the great success of graph neural networks, graph-based paradigm mainly relies on GNN-based methods or hypergraph neural networks-based methods. It aims to capture collaborative signals and model complex relationships among high-order neighbors and has achieved considerable performances in NetSPI recommendation. For example, in GNN-based works, researchers model complex POI and POI complex relationship and etc. to gain a better representations of POI. Hypergraph is a generalization of graph, where an hyperedge connects two or more vertices. Thus, hypergraph can model beyond pairwise relationship to solve the limitation of normal graph. Despite effectiveness of mentioned approaches, two key issues still remain less explored. First, most previous studies have ignored the fact that user preferences are diverse and constantly changing in terms of various aspects, leading to entangled and suboptimal user representations. Considering the scenario depicted in this image, when a user selects a restaurant, it's crucial to analyze the decision factors, such as the category of the POI, temporal aspects, and geographical considerations that affect their behaviors for mining purposes. The second limitation is that many existing methods have inadequately modeled the crucial cooperative associations between different aspects, hindering the ability to capture complementary recommendation effects during the learning process. In NetSPI recommendation, some researchers have adopted multi-view learning or disentangled learning paradigm to learn view-specific or aspect-specific representations separately, and simple fuse them for NetSPI prediction. However, such methods fail to differentiate the similarities among views or aspects. Additionally, few existing words only consider the cooperative associations at the level of prediction, resulting in no mature enhancement among the views is guaranteed to be captured. Before introducing our proposed framework DCHL, we firstly give a task formulation. We've got user set, POI set, coordinates for each POI, and each user's trajectory. Given a target user and her trajectory, The goal of next POI recommendation is to recommend top K POIs that the user may visit in the next timestamp. To this end, we propose the Disentangled Contrastive Hypergraph Learning DCHL framework. It mainly consists of 4 parts. The first one is the model input part, takes users checking records as input. And the second is the multiple disentangled hypergraph learning component to disentangle intrinsic aspects among collaborative, transitional, and geographical views. The third part is the adaptive fusion and cross-view contrastive learning, and the final part is the prediction. Let's move to the multiple disentangled hypergraph learning part. We firstly elaborate on the construction of multiple disentangled hypergraphs from collaborative, transitional, and geographical views, and decide hypergraph convolutional networks with adjusted aggregation and propagation methods to decouple intrinsic aspects. The construction of the collaborative view hypergraph involves building a hypergraph that captures high-order collaborative signals between the users and POIs. In the hypergraph GC, we represent each user's trajectory SU as a hyperedge. So the hyperedge set consists of all users' trajectories. Additionally, incidence matrix HC is introduced to describe the user and POI interactions. Collaborative hypergraph convolutional network involves 2 states. The first is the intra-hyperedge aggregation. For the hyperedge E, we aggregate its member POI embeddings to generate the median message embeddings. Here, the AGG node-to-edge function is to generate the denotes node-to-hyperedge aggregation function. Since each node L may belong to several hyperedges in this stage, we aggregate the message from related hyperedges to refine the representation of the node. By stacking L layers, we apply residual connections to alleviate the over-smoothing issue of GNNs. The construction of the transitional wheel hypergraph involves building a hypergraph that captures directly transitional relationships between the POIs in all trajectories. In the hypergraph GT, we represent target POIs as hyperedges, and the source POIs are nodes in the hyperedge. Different from the collaborative hypergraph convolutional network, transitional hypergraph convolutional network needs to capture the directed relationship. At the first stage, it aggregates source node embeddings to form the hyperedge embeddings. Since the propagation is directed, we cannot propagate the target information to the source. We take the median hyperedge embeddings as source and aggregate message from related hyperedges and propagate to the target node embeddings. We also apply residual connections here. For geographical hypergraph, we firstly calculate the POI and POI geographical distance with coordinates and Haversine distance, for our Earth is a sphere. If the distance is less than the threshold, we set 1 in the insistence matrix, otherwise 0. The message passing scheme also contains 2 stages, node to hyperedge aggregation and hyperedge to hyperedge message switching, and propagate to the node. After that, we perform the adaptive fusion for user representation. Here, we first perform the disentangled user representation by leveraging the incidence matrix HC, the transpose of the HC, and we get the each aspect's user representations in the collaborative, transitional, and geographical view. After that, we perform the adaptive fusion for the user representation by a lambda C, lambda T, and lambda G by designing the adaptive gate. After that, we sum the POI representation from the collaborative, transitional, and geographical view to form the final fusion POI representation. After that, we perform the cross-view contrastive learning by the info NCE lost. And we take the same user's representation from the collaborative and transitional or the geographical as the positive sample, and the different users' representation from the collaborative or the transitional as the negative sample. After that, we could get the total contrastive learning loss. Here is the data set. We used the two data sets from the Foursquare New York City and Tokyo. And we also performed the experiments on the industrial scenarios data sets Meituan. We also choose some baselines from several categories, like statistical, RNN-based, self-attention-based, GNN-based, hypergraph-based, and graph or hypergraph contrastive learning-based. Here's the main result of our DCHL against the various baselines. We could find that our DCHL consistently outperforms all baselines on 3 datasets. In terms of all evaluation metrics, we choose the recall and NDCG here, and the K is 5 and 10. We contribute the improvements to the following aspects. The first one is by considering collaborative, transitional, and geographical views while disentangled hypergraph learning, our DCHL disentangles multi-view user preferences that drive their behaviors and alleviates the data sparsity issue. The second one is benefiting from our design cross-view contrastive learning schema. Our DCHL can self-augment learned with specific representations, and this to supervision signals for capturing complementary recommendation effects during the learning process. We also perform ablation study to validate each part of our DCHL by removing each part and keep the rest. When removing collaborative view, performance dropped clearly. It strongly indicates the importance of modeling user and POI interactions, for it can distill higher order collaborative signals. Since Meituan dataset is much sparser than New York City and the Tokyo datasets, capturing global transitional relationship helps alleviate the data sparsity issue. We also compare our designed adaptive fusion methods with other information fusion methods. For example, summation, concatenation, and attention. It also shows the effectiveness against other fusion methods. We also perform the user co-star performance. We choose the top 15 frequent users as the most active user group, the bottom 15% as inactive user group, and the rest are normal users. From the figure 3, C and D, benefiting from learned embeddings, normal user group achieves better results compared with that without trained embeddings on sparser and larger Meituan dataset. It provides some solutions when dealing with large-scale graphs or hypergraphs in practical industrial scenarios. We also performed some in-depth analysis by replacing our designed hypergraph convolutional networks by replacing by HGNN plus and light GCN, and it shows the effectiveness of our DCHL. Here's the conclusion part. We performed the disentangled hypergraph learning to decouple intrinsic aspects among collaborative, transitional, and geographical views with adjusted aggregation and propagation methods. We introduced cross-view contrastive learning with self-augmentation for capturing complementary effects. Experimental results on 3 datasets demonstrate the effectiveness of our DCHL. For the future work, we will try the implicit disentangled learning method or the interpretable user decisions modeling and recommendation. Here's my presentation, and thank you so much. Thank you so much.